Welcome back to the deep dive. Ever stared at a frozen UI, or maybe you're trying to figure out how to really make that multi-core CPU sweat using C Sharp?
Yeah, if that sounds familiar, then stick around.
Today we're digging into something that, well, let's be honest, can feel a bit intimidating for developers.
Mm.
Task programming in C Sharp.
Right, the Task Parallel Library, or TPL. Our mission today is pretty straightforward. Give you a shortcut to really getting it. This stuff is the foundation for modern async programming in .NET.
We're not just talking definitions. We want to show you what tasks are, how they work, but also, critically, the traps to avoid.
Exactly. The goal is building software that's, snappy, responsive, efficient, and actually uses all that hardware power.
So let's kick off with an analogy. Our sources use the working mother analogy. It kind of sets the scene.
It does. Picture this.
Yeah.
She needs to get ready for work and make a full breakfast. 2 big jobs.
Oh, okay.
So she starts the water boiling for coffee. But does she just stand there watching it? No way.
Right. She's got other things to do.
Exactly.
Yeah.
She immediately switches to helping the kids get dressed. She's interleaving tasks. She starts one, maybe hits a waiting point like the kettle boiling, an I/O wait, and pivots to something else, maybe more CPU intensive like wrestling kids into coats.
And then back to the kitchen later.
Right.
Yeah.
That constant shifting, avoiding just sitting idle waiting. That's the core idea of doing things asynchronously.
Okay. That makes the responsiveness goal really clear.
Yeah.
But let's nail down the terminology. Is that asynchronous shifting the same as parallelism?
Good question. No, they're different, and it trips people up. Asynchronous is mostly about efficiency, maybe even on just one core, like that parent juggling rice cooking and homework checking.
The goal is not blocking.
Yeah.
Keeping things moving.
Precisely.
Yeah.
Keeping the UI thread free, keeping the application responsive.
And parallelism then.
That's when work is genuinely happening at the exact same time. Different people, or crucially different CPU cores, handling separate jobs simultaneously. Cook makes rice, parent checks homework, literally side by side. Our source material actually calls asynchronous programming a means of parallel programming. It's a technique to run work separately from the main flow, which enables parallelism if you have the cores.
And this used to be way harder, right? Developers juggling raw threads, those old sync result patterns. Kind of messy.
Oh, incredibly messy and error-prone. That's why the TPL, introduced back in .NET 4, was such a game changer. It simplified all that complexity.
So now we use the task-based asynchronous pattern, TAP.
Exactly, built on task and past result. These tasks are like lightweight wrappers around work that often runs on the thread pool. They give us control without needing to micromanage the threads themselves. It's the standard now.
Okay, so tasks are fundamental. How do we actually kick one off? Our sources mention 3 main ways, but one seems heavily preferred.
That's right. Look, for probably 90% of your typical CPU-bound work, you just want task. Run. You pass it your method or Lambda, like task, run to do some work.
Why that one specifically?
It's designed to safely queue work to the .NET thread pool. It handles scheduling details correctly, especially important for, responsiveness and avoiding weird threading issues. Simple, effective.
What about the others? Task.factory.startNew? I see that sometimes.
You do, but it's trickier. Start New gives you a lot more knobs to turn schedulers, creation options. But it's easy to misuse those options, especially if you're chaining tasks together later. It could lead to subtle bugs.
So maybe avoid it unless you really know why you need that extra control.
Generally, yeah. Stick with task, run as your default. The third way, new task.factory in the start, is even more manual. You create the task object, then you have to explicitly call start. It's just less convenient.
Makes sense. And tasks aren't just fire and forget, right? They can take input, return results using task result.
Of course. You pass data in via closures or state objects and get results back asynchronously using the generic task type.
But here comes the big warning sign flashing red lights. The sync trap.
Ah, yes. This is probably the #1 mistake people make when starting with tasks. It's where all your async good intentions can just evaporate.
How does it happen?
It happens the moment you use the .wait method on a task, or you try to access its .result property directly.
What does that do?
It forces the thread that called it often your main UI thread or a web server request thread to just stop, freeze, block completely until that background task finishes.
So I kick off a network call with task, run, then immediately ask for result.
Boom. You just made your asynchronous code synchronous again. All the responsiveness benefits gone. You've essentially just blocked the calling thread, potentially leading to deadlocks, especially in UI or ASP.NET contexts.
We call it a trap because Dart result looks so easy, so tempting.
Exactly. It feels natural if you're used to synchronous code, but it completely undermines the async pattern. Only use flat result if you have absolutely no other way to proceed and you fully understand the risks, especially deadlocks.
Okay, that blocking danger leads us right into managing time properly. If we need a pause in our code, how do we wait without locking everything up?
Right, we need to distinguish blocking delays from non-blocking ones. The old way, the brute force way, is thread sleep 1000.
That just halts the current thread, right? Nothing
Love
else
it.
happens on it.
Correct. It's a synchronous pause. Generally, you want to avoid this in modern async code, especially anywhere near UI.
So for responsive apps, the tool is task delay 1000.
That's the one. Task delay is async friendly. It returns a task that completes after the specified time, but crucially, it doesn't block the current thread. The thread is released back to the pool to do other work while the delay is happening.
Makes the UI feel smooth.
Exactly. Keeps things responsive.
Okay, now what about managing groups? Say I fire off 5 different tasks. How do I know when they're done? We saw blocking options first. Task, wait all.
Right. Task. Waitall takes an array of tasks and blocks the calling thread until every single one of them has completed.
And taska wait me. Similar idea, but it blocks only until at least one of the tasks in the array finishes. It returns the index of the task that completed first.
But you flagged a serious gotcha with waitney, didn't you? Something about exceptions.
Yes, this is critical. If the task that finishes first completed because it threw an exception, waiting doesn't automatically throw that exception back at you. It just happily returns the index of the completed faulted task.
Whoa. So if I just call waitney and don't check the status of the task it points to, I could be completely missing an error.
Precisely. The exception gets swallowed unless you explicitly check task is faulted or try to access its result later. It's quite subtle.
That sounds like a recipe for hidden bugs.
It can be. And that's why, honestly, unless you have a very specific reason why you must block the calling thread, the much preferred approach is the non-blocking alternative, task. When any
different.
task. When any also takes an array of tasks, but it returns another task, a task that completes when any of the input tasks complete. Because it returns a task, you naturally await it, staying in the async world. And await handles exceptions properly.
Yes. Awaiting the result of when any, which is the task that completed, will correctly propagate any exception from that task. It forces you into a safer pattern. Use when any over waiting for responsiveness and better error handling.
That's a really important distinction. Okay, moving beyond just waiting. TPL lets us chain work together, right? Continuations.
Yep, using the continue with method. This lets you say, okay, when task A finishes, then automatically start task B. You attach a follow-up action.
And that's how you pass results or handle errors from task A and task B without blocking.
Exactly. It's the structured, non-blocking way to sequence async operations.
And you can add logic here too, conditional continuations.
Absolutely. Task continuation options gives you fine-grained control. You could say, only run this continuation if the first task finished successfully, using not unfaulted.
Or the opposite, run only if it failed.
Right. Only unfaulted is perfect for running cleanup logic or logging an error, but only if the preceding task actually threw an exception. Very useful for building robust workflows.
Let's talk nesting. Tasks inside tasks. What's this detached versus attached child task thing?
Okay, think of it like responsibility. A detached child task is like an independent contractor. It starts, does its thing, and finishes whenever. The parent task might finish long before the detached child does.
They run separately.
Completely. But an attached child task, created using task creation options, attached to parent is different. It's like tied to the parent's fate.
How so?
The parent task cannot signal that it's complete until all of its attached children have also completed. If you wait on the parent, you're implicitly waiting for the attached children too. It enforces dependencies.
Okay, that makes sense for certain workflows. And one more nesting thing, the unwrapping mystery. What's task result?
Haha, yeah, that looks weird. Sometimes an async operation itself returns a task. For example, task run might return a task that represents starting another operation, so you end up with a task of a task.
Seems complicated to get the final result.
It would be, but there's a helper, the unwrap extension method. You call it on the outer task result, and it gives you back a simple task result that represents the completion of the inner task. It just simplifies getting the final value. Await actually does this unwrapping implicitly most of the time now too.
Nice. Okay, essential part of robust apps, handling errors. With tasks potentially running in parallel, what happens if multiple tasks throw exceptions? Does the first one just crash the app?
Nope. And this is a major difference from synchronous code. Exceptions thrown inside tasks don't immediately bubble up. They sort of
Look
collect.
where?
They get bundled together inside a special container exception called AggregateException. This wrapper only gets thrown later, typically when you do something that forces waiting, like calling wait
Hmm.
or accessing result.
So if 5 tasks fail concurrently, I don't get 5 separate crashes. I get one aggregate exception.
Exactly. And inside that aggregate exception, there's a property called inner exceptions, which is a collection containing all the original exceptions from the failed tasks.
How do you handle that? Loop through them?
You can. You can iterate through inner exceptions and log them or try to handle them. But a more sophisticated way is using the aggregate exceptions handle method.
What does that do?
It takes a delegate function that receives each inner exception one by one. Inside that function, you decide if you can handle that specific exception type. If you can handle it, you return true.
And if you can't?
If you encounter an exception you don't know how to handle, you return false from the delegate. Any exception that gets a false is repackaged into a new aggregate exception, which then gets thrown up the call stack. It lets you handle what you expect and safely propagate the unexpected.
Very cool. Okay, switching gears to planned stops. Cancellation. We have to stress this. TPL cancellation is cooperative, right?
Absolutely fundamental point.
Yeah.
It's not a magic kill button. You request cancellation using a cancellation token, but the running task has to actively check that token and decide to stop itself.
The task has to play along.
It has to cooperate. And how it stops actually matters for its final status.
What do you mean?
We'll imagine a task checks the token, sees cancellation was requested, and just returns. It exits cleanly. What status do you think that task reports?
Ran to completion because it finished without error.
Exactly. Which is misleading if you wanted to know it stopped because of the cancellation request.
Well, how do you get the canceled status?
The task needs to acknowledge the cancellation by throwing a specific exception. Operation canceled exception. It should ideally pass the token it was observing into the exceptions constructor.
Okay, so check token. If requested, throw operation cancel exception.
Correct. And there's a handy shortcut method. Throw if cancellation requested on the token itself. It does the check and throws the correct exception for you in one line. It's the standard best practice.
Nice and clean. What about multiple reasons for cancellation, like the user clicks cancel or R and timeout expires?
Yeah, you can handle that using cancellation token source.cried, create linked token source. It lets you create a new token source that gets canceled if any of the original sources is linked to or canceled. Very flexible.
All right, great stuff on control flow. Before we wrap up, let's hit a few quick next-level tools for really polished task management. First up, progress reporting.
Yeah. Crucial if you have tasks that take more than a couple of seconds. Users get nervous if they don't see something happening.
How do you report progress back safely, especially to the UI thread?
You use the iProgressT interface. The common implementation is the ProgressT class. You create an instance of ProgressT, usually passing a delegate and action T in its constructor. That delegate is what actually updates the UI, say a progress bar.
And ProgressT handles the tricky part of getting that update onto the right thread.
Yes, it automatically marshals the callback to the synchronization context where it was created, which is typically the UI thread. So you just call progress.report some value from your background task, and the UI updates safely.
Yeah. Okay, next tool. Implicit parallelism with the parallel class.
This is like the easy button for simple parallel execution. If you just have a bunch of independent methods, actions you want to run concurrently, maybe some heavy calculations, you can just call parallel.invoke. Action 1, Action 2, Action 3. TPL handles creating the tasks, running them potentially on multiple cores, and waiting for them all to finish before returning. Super simple for straightforward CPU-bound parallel work.
Candy. And the caching shortcut, using pre-computed tasks.
Oh, this is a great performance win. Imagine you have a function that calculates something expensive, but the result doesn't change often.
Like fetching configuration data or something.
Exactly. The first time you run the actual task, calculate the value and cache it. But the next time someone asks for it, if you already have the value in your cache,
Don't run the task again.
right, just immediately return an already completed task containing the cached value.
Yeah.
You do this with task from result, cached value. The calling code awaits it just like any other task, but it completes instantly. Our sources show this dropping multi-second calls down to like 1 millisecond. Huge win.
Very cool performance trick. Okay, last one, briefly. Task completion source result. Sounds a bit advanced.
It is powerful, but it solves a specific problem. It's 4 situations where you want to create a task, but you manually control when that task completes, fails, or is canceled. It's not tied directly to a running piece of code.
Why would you need that?
Think about integrating with older event-based systems. Maybe you start an operation and you'll get an event later when it's done. Task completion source lets you create a task up front, return it, and then later, when the event fires, you call set result or set canceled on the task completion source object. That completes the task you returned earlier. It bridges the gap between external events and the TPL world.
Got it. Sort of like a promise you fulfill later.
Exactly. It's the producer side of a manually controlled task.
Wow, okay. That was a really thorough deep dive.
Oh,
So, to quickly recap the absolute must-knows, tasks via TTL are the way forward for async in C#. Lightweight, manageable.
and the biggest thing is avoiding that sync trap. Don't call, wait, don't access a result unless you have zero choice and know the deadlock risks. Responsiveness depends on it.
Use the non-blocking tools. Task delay, task done any, sequence work with continue with. And remember, cancellation is cooperative token. Check the token, throw operation canceled exception.
Get those fundamentals right, and you're moving from potentially clunky blocking code to applications that really fly on modern hardware.
It's the difference between frustrating users and delighting them.
Couldn't agree more. Now, maybe one final thing for listeners to chew on.
Go for it.
Okay, so we hammered home that calling result is bad because it blocks. But think about overhead. Tasks are lightweight, sure, but creating thousands or millions of tiny, very short-lived tasks using task. Run isn't free either. There's scheduling overhead, context switching.
Right.
So if you have, say, 100 tiny calculations, it's wrapping each one in task. Run, always the best way to use parallelism. Or could the overhead of managing all those tiny tasks actually make it slower than just running them synchronously in a few batches? It's the balancing act. Sometimes less is more, even with tasks. Something to think about.